Okay, so it is a great pleasure and honor to host today Rida Laraki. He's a professor at the Université Paris-Dauphine and in Liverpool, and from the day after tomorrow, he will also be a professor at the University of Mohammed VI in Rabat. So Rida completed his PhD in mathematics in 2000 at the Université Pierre and Marie Curie. And he started his academic life studying repeated games with incomplete information. Afterwards, he studied with Michel Balinsky. He studied majority judgment and promoted its actual use. And he was one of the founders of the non-for-profit organization Mieux Voter, Vote Better. So on top of these two topics, Rida made important contributions to other areas in game theory, like stopping games and games with discontinuous payoffs. He authored 3 books, both introductory level game theory books and a book on majority judgment. And he's also a member of several editorial boards of game theory journals. And so it is an honor to have him speak today on majority voting, judgment, sorry. So Rida.
Thanks, Ellen. So it's a pleasure to be with you. So it's a work about belief aggregation, and at the end I will explain how this can be connected to majority judgment work. But at the beginning, so there is no connection. It's really, let's say, it's almost independent from voting and majority judgment theory. So yeah, as Ellen said, I will be joining as affiliated professor at University Mohammed VI Polytechnic, and my objective is to create an international game theory center where we're going to hire many people and hopefully organize several conferences and events. And I hope I will see many of you visiting Rabat and Morocco. If you don't know Morocco, you will be fascinated by this beautiful country. And yeah, I'm looking forward to see all of you. So this is a joint work with my PhD student, Estelle Varlo. She's finishing her PhD in Liverpool. So the motivation, many decision makers, for example, Federal Drug Authority, have a committee of experts that give their opinions before, to the decision maker, and then a decision is made. In the case of Federal Drug Authority, FDA, they use a voting system to do so. This is, and in many instances, experts are uncertain about their predictions. And so they for example, for volcanic eruption, so it's very difficult to predict when a volcano will have an eruption. And what they do is they ask several experts their probabilities, and then they try to aggregate these probabilities to one probability. So this will be the topic of my talk today. And this is a social choice theory problem, and where I am interested, coming from game theory, by strategy proofness, meaning have the option that so that to have a mechanism such that experts will report truthfully their preferences or their probabilities. So for that, we need to define the utility function in a proper way, and this definition is important to have existence. As a motivation is, for example, there are many controversies when you have experts intervening, of conflicts of interests, of misreporting, of manipulation of information, and I think there is having a strategy proof rule is an important problem in practice. So to be formal, some suggest to keep idea fixed. So what we have is an outcome space lambda. X expert I in a set of n experts will report his pick, his prior probability distribution, PI, so or subjective probability. Delta of lambda is the set of probability distributions over the set of outcomes lambda. So this is the input. And then what we want is to design what I'm going to call a probability aggregation function, which will have some nice strategic properties, so strategy proofness. So we have n inputs and probabilities from the experts, and the output will be a probability. So there is a huge literature when monetary transfers are possible, conditional on the realization. So experts will predict, and then we're going to reward them depending on the realization. And so to motivate them, there will be some scoring rule for the monetary transfers. So this is a huge literature that I'm not going to talk about because I will be mainly interested by voting situations where there is no monetary transfers. So for example, for volcanic eruptions, the events are very rare and it's very difficult to condition on that. Also, sometimes the consequences are very catastrophic and there is no time, there is no learning. And we would like, there is no, so this is not an option to do monetary transfers. So that's the idea. Okay, so this problem has been studied in literature by many economists as a special case of the budget aggregation problem. So imagine you have a budget to distribute between different projects. So each expert or each voter will say, okay, I would like, for example, 20% of the budget to be allocated to economy, 45% to defense, whatever, and the sum is 100% of the total budget. So this is like a probability, mathematically speaking, and so this is a combinatorial domain, if you want, and the conclusion is usually negative, meaning that even if we restrict the preferences to be single peaked, so meaning that there is a peak that the expert would like to have, or each expert has its probability or his preferred probability, or the probability coming from his model that he's using to predict, and you would like the final outcome to be as close as possible to this probability. So if we suppose that preferences are rich enough, and here rich, for example, it can be the class of all convex preferences over delta over P, or it can be additive separable convex preferences over P. So if the space is large enough, then there is no strategy proof single peaked in this domain. But much more recently, so there is a paper who provides a family of methods called phantom moving mechanisms that are strategy proof in the budget aggregation problem when the domain of preferences is, I would say, severely restricted to single peak preferences with respect to the L1 distance over the probabilities. Okay, so to be more precise, the utility function of each voter will be the minus the distance, the L1 distance between the peak of the voter and the outputs of the mechanism. Okay, so to be precise, if K is index of the events, so you have Pk minus Qk, absolute value, sum over K. Okay, this will be the L1 distance between two probabilities P and Q, and you take minus this, and this will define the utility function of the voter. Okay, under this assumption, there are many mechanisms. They call them phantom moving mechanisms. Okay, and these mechanisms will be strategy proof with respect to this L1 distance. In fact, you can prove that they are not, the same mechanisms are not strategy proof if you take, for example, the L2 distance or LQ distance with Q strictly higher than 1. So this is really specific to the L1 distance, and you can also prove that it's impossible to find single peak, to find strategy proof mechanisms for another distance than the L1 distance. So it's very, very specific to this distance, and that's the results in this paper. So my point here is that if our problem is so I'm going to give immediately why my statement here is true, is that if you take the L1 distance over the probabilities or any LQ distance over the probabilities, then in many applications this distance of preferences to model the preferences or to model the single peak preferences is not the right distance. And I'm going to give an example. So suppose that you have lambda is a finitely ordered set. So for example, think to the Richter scale for earthquakes. So this is the less dangerous level. This is the highest dangerous level. Okay. So this is the set of outcomes. So imagine. So this let's do the exercise. That's agent I inputs. So he thinks that there is no risk. So he completely sure that the probability of an earthquake is really the minimal one, delta, the Dirac mass at the smallest possible level. And suppose that the output would be two options, or it is the Dirac mass at A2, or it is the Dirac mass at the highest level AM. Okay, so we intuitively we would like to if he thinks that it is this level and the output is this level, he's more happy than if the output is this level, the highest level. Okay, so the distance between the fact that this is an ordered set implies that this point is closer to this one than this point to this one, and consequently the probability, the Dirac mass at A1 should be closer to the probability, the Dirac mass at A2 compared to this Dirac to this Dirac. However, if you take any LQ distance, in particular the L1 distance, this quantity and this quantity are exactly the same. Why? Because usually, so if you have M outcome, like here, you are going to embed this in an Euclidean space of M dimensions. You have unit vectors for each one of them, and the distance between this unit vector and this unit vector will be for the L1 distance equal to 2, and this will be also equal to 2. So there is no way to distinguish between these two quantities with the L1 distance or the LQ distance, which is not natural if this is the set of outcomes. Of course, this is not an example of in this related to this paper, because here they are doing budget aggregation, and the outcome space in this case is not an ordered set. This is really independent objects. Okay, these are really independent. For example, defense, economy, and if we think about a political decision, so these are independent dimensions, and it makes sense that we treat them independently, and this distance in that case makes sense. But if we are doing, for example, prediction in some ordered set, for example, what is the increase of temperature in 5 years, 10 years, we ask several experts of climate change, they will. This is the outcome is in a space which is ordered, okay, and the expert will not agree probably on the increase of temperature in 5, 10 or 20 years, and we would like to aggregate this probability, and we are in our model, and we would like to find the right way to model single peak preferences there. And so the solution I propose is, instead of measuring the distances with respect in the P space, let's do it in the cumulative distribution space, the CDFs. And this makes sense here because it's another set that you can compute easily the CDF. And here clearly, if you compare the CDF introduced by this Dirac and this Dirac, they will be much closer than this Dirac to this Dirac. Okay, so this is what we are going to do in our paper. We are going to suppose that we are single peaked in the space of cumulative distributions and not in the space of probability distributions, and this will change completely everything. Okay. Any question? So now, what are
yes, I've got a question, if I may.
Yes.
Is it convenient that I ask now, or shall I wait? Shall I wait till the end?
If it is as you prefer.
Then I would like to ask now. So could you please go one slide back? The first bullet point, I just wanted to clarify.
Yes.
Basically, you assume that every participant provides a distribution, and the utility of the participant is dependent on the distance between their distribution and the one which is aggregated.
Yes.
Is that the model?
Sorry?
Is your model basically assuming that there is a game between the participants?
Yes.
And each participant aims to minimize the distance between their distribution and the one which is aggregated.
Yeah.
But how can you capture the possible strategizing where they like some distribution, they provide another distribution to have yet another one aggregated? So how can you, where do you have this desired distribution in the utility?
So yeah, what I mean here is, so to be precise, you have some distance, let me take another color. So we have some, the model you should keep in mind is the following. The PI is the probability distribution of agent I. We have some distance, okay, between PI and the aggregation. The aggregation will be P of everybody, P1, okay, and I take minus the distance of this, and I suppose that this is the utility function of voter I if he has PI and the others are P minus I. Okay, this is the model.
Can you please repeat what is the mu? What is the last thing you have just?
Of P1 Pn is I, the utility of agent I. So just I didn't write it very well. U of UI of agent I.
I see.
And is in PI, the other probabilities of the other players, and this will be kind of minus the distance of PI to the aggregation.
Then my question is basically, I would suppose, I probably am wrong, but that's what I'm asking about. I would suppose that every player has the distribution they believe is true.
Yeah, this is this one.
And this is the PI. Now, then they might, perhaps strategically.
Well, let me stretch it. I didn't write it well. I understand what you mean.
So
the will depend on sorry. He thinks that it's PI and his input QI. Okay.
Okay.
Okay. So he, of course, he think it's PI, and what happens if he reports QI? Okay.
And the goal is, of course, to make the game such that reporting the truth is weakly dominant.
Exactly. Yeah, that's the objective. Okay.
And then the last clarification point, please. The distance you are talking about, that's exactly the discussion which you made.
Yes. Depending on which distance you put here, you will have possibility, impossibility, and what I claim is if you check the distance in the probability space, L1 distance, then you are in this paper here. Okay. If you check the L2 distance, then it will be impossible.
Yeah.
And I'm going to take the distance in the cumulative space.
Okay. So the QI now, the QI is the private.
Yes, it's private. The private.
Okay. Thank you.
Rida, 1 second. Your answer confuses me a little bit. So QI is the true evaluation?
No, PI is the true. Sorry. QI is the true. Let me write it differently. Sorry. So yeah, PI is the wrong and QI is the true. Let's say.
Okay. So my utility is not from the way I am perceived, but the way I feel myself inside myself. I know that I mean the outcome is close to me to my projection, even though I reported something completely else, and so the public gives me a completely different utility than what I give myself.
Yes.
So you should put the QI in the distance in the first place. Am I right? Or is it already QI? I'm just misreading that.
No, sorry, just here what I just, so here, if I report PI, sorry, if I report PI, so sorry, it should be QI here.
Exactly, yes.
QI here and
PI inside the psi.
Yeah, QI is my private value, which is it's my private value, which is here, and PI is what I report.
Okay.
Okay.
Thanks.
So now, so I should have written this more carefully. Okay. Sorry. Is this clear now, the model?
Yeah, it is.
Good. So now what we do is we define something. We are going to call it level strategy proofness. Okay. And this implies classical strategy proofness in the sense of the definition I just wrote before. So it will be where for a rich class of single peak preferences, meaning that it will be strategy proof for all distances LQ in the cumulative space. Not only L1, it will be L or LQ Q positive. Okay. So level SP implies classical strategy proofness for every LQ distance in the cumulative space C. Okay, that's the implication of this. So this is a strong notion. I don't want to fix some particular distance. I want to let this space rich enough. Okay, now, some player may have L1 distance, other player L2 distance, whatever they want, and I want this to be true for a large class of possible distances. Then we're going to characterize all the level strategy proof probability aggregation functions plus some axioms I'm going to add. This will imply that I'm going to characterize two possible interesting solutions to the problem. One, I will call it the Middlemost cumulative solution, and the other one, I will call it the proportional cumulative solution. And this proportional cumulative solution will be interesting by itself because it will allow me to extend a method of voting that I designed with Michel Balisky, and we call it majority judgment. So to uncertainty in the sense that now voters will not say this candidate is great for sure. They may say, I think this candidate will be great with probability 1/2 and will be terrible with probability 1/2. So which I think is more closer to what we feel about elections. We are never sure that someone will be a good candidate. We think he can be good, but he may not be good. And we can model this with probabilities. Okay, so I'm coming to this at the end. Okay, now, very important, if you want to understand the results, you should, I must recall the very important results of Hervé Moulin for single peak, for aggregation in the very basic one-dimensional setting. So here there is a location problem, 0, 1. For example, we would like to have a store somewhere here, and each voter would like the store to be as close as possible to his house, let's say. So utilities of voters are in the interval 0, 1. We say that the utility is single peaked if there is some element X, which is the peak of the voter, such that if you are more closer to X, the more the voter is happy. Okay, so the utility will be somehow the increasing and decreasing with respect to this peak. And now we're going, so we call it one-dimensional strategy proofness, 1SP. A voting rule, here we are in the very simple space where each voter gives a number between 0 and 1. And so we have n voters, and we would like to output a number between 0 and 1. And we call it one-dimensional strategy proof if reporting the real value, my real peak as a voter is a dominant strategy. And it can be proved that this is completely equivalent to a property called uncompromissedness. So what is uncompromissedness? It tells you that if voters' input is strictly smaller than the aggregation, and he changes input from Ri to R prime I, he cannot, okay, he can only be higher than the final, he can be only higher than the aggregation. So to be more precise, imagine you are given, so here it's the final location if it's an allocation problem, and you want your value is strictly smaller than the allocation, the final allocation. So you would like to decrease this value. You cannot, because if you lie, you can only increase the value and you cannot decrease it to make it closer to your input value. And similarly, if you are bigger, okay. So this property is equivalent to strategy proofness, and you will see later that level strategy proofness is somehow very close to this property in its definition. Now I'm going to have two axioms that I'm going to suppose. Anonymity tells that all voters are treated similarly by the mechanism, meaning that if I permute the name of the voter, the aggregation will be the same. Okay. And unanimity says that if everybody agree that the final value should be R, then it is R. Okay, so that's two axioms I'm going to suppose. And so Hervé Moulin in 81, he characterized, it's in public choice, the paper, characterizes all strategy proof methods, one-dimensional strategy proof methods that are anonymous. So how you construct them? It is sufficient to take n+1 values in 0, 1. You call them phantom. He called them phantom voters in his paper, and then you take the median between the n values, the n input values by the voters, and the n+1 phantom values that are fixed and doesn't depend on these values. So it gives you two n+1 value. So it's an odd number. So you take the median of this, and it will be the output of the mechanism. Okay, and for the mechanism to be unanimous, it is sufficient to have this value equal 0 and this value equal 1, which implies that we can drop them from the median and just consider n-1 values, phantom values, and you take the median of these values to compute the output. So this is the Moulin's result, and having this result in mind, you understand very quickly what we are doing and our characterization. Good. So now let's move to our model. So we'll have n experts. Cardinality is small n. Lambda will be the set of outcomes, and we're going to suppose it's linearly ordered set of alternatives. Typically, lambda will be an interval or a finite set in applications. But let's suppose it to be any Borel subset of R. And P will be the set of probability distribution over lambda. So this will be the input space for every voter. And C will be the set of cumulative distributions over lambda. Okay, so and now we are going to have a mapping pi, which will be a bijection that maps a probability to its cumulative. And for example, if small p is the probability of some, if it is a probability on lambda, then this is just the probability to be smaller or equal to A, the cumulative at A, and we are going to denote it by capital P instead of small p. Okay, this is small p, this is capital P. So so we can ask voters to submit their probabilities, or equivalently, we can also ask them to submit their cumulatives. Okay, so it's the same. So we can, the model can be, so we have to, and we are going to move from one to the other when we are going to introduce our axioms or our characterization. So P is the probability input profile. It's in bold, and capital P in bold is a CDF input profile. It's in the space of cumulatives. This is the space of probabilities. And this is the profile of all experts except voter I. Okay. So this is classical notation in game theory. Now, now the main definition, what I'm going to call level strategy proofness. What is level strategy proofness? It's the following property. So probability aggregation function psi will be called level strategy proof if I take any level A. Okay. This is the cumulative probability up to A for voter I. So if the cumulative probability, for example, what is the probability that the temperature will not exceed some 5 degrees, if A is 5 degrees, okay, A is equal to 5 degrees Celsius. This is the total probability. This is the total probability that it will not exceed 5 degrees. If this voter believe that this is small, if this total probability is smaller than the aggregate probability, then by lying, the voter cannot increase the cumulative at A. And similarly, for if his probability is higher than the output, the cumulative at A is higher than the aggregation of the cumulative at A, then the voter by lying can only decrease. So this is you see that this is similar to the property of uncompromissedness of Jordan and Border. What is important here is this should be true for every level A. So take any level A, this property must be satisfied. So this is a definition. Now the question is what is the relation between this definition and strategy proofness? The classical strategy proofness given by utility functions. And what we can show is the following. If a probability aggregation function satisfies level strategy proofness, then it will be strategy proof in the classical sense for all single peak preferences in which utilities are measured as using an LQ distance to the peak, but in the cumulative space. Okay, so meaning so the formula I wrote before, where the distance is taken in the cumulative space, not in the probability space, and take any LQ distance you want. Okay, and voter may not have the same using the same Q. So each voter may have his particular Q if you prefer that. So this is very strong because it tells you that if this is true, then you will be strategy proof for a large class of utilities. It's in a rich space of utilities. Okay. And something important to keep in mind is that it is impossible to be level strategy proof and also strategy proof for the L1 distance on the probability space. So this is the paper that I discussed of Freeman and co-authors, which was published in EC and JET last year. So they characterize a branch of methods that are strategy proof for L1 distance in P. Okay, but these methods are not level SP, and level SP method are not strategy proof in the L for their according to their definition. So we are not discussing and we are not characterizing the same set of methods. Okay,
Mike, I've got a question, if I may. Is it fine?
Yes, of course. Yeah.
My question is a bit harken back to what I was asking then. So it seems that you need this Q, this private value somewhere, because you want to say that if you would like something to happen, you are not able to make it happen. So shouldn't it be like pi of QIA?
Sorry, this Q has nothing to do with it's not a point, it's just a parameter for the distance. So here it's L1 distance, L2 distance, LP. It's not a Q probability. So sorry if it's confusing. Let me call it L, I don't know. Any distance in the sense of, the distances in Euclidean spaces, you see?
Then could you please just clarify once more what the pi of Pi of A means? So what does pi of Pi?
This is what is written here. Here.
The cumulative probability.
Yeah.
Of being below
threshold. So for every threshold A, okay, this is the cumulative probability of voter I.
Here I have a question. So the gist of my question is, this cumulative probability, is it calculated with respect to the private?
Yes. So this is not important because this is how to say. So imagine that everybody is reporting that. So how to say? This is not important because if it is your private value, okay, if it is your private value, do you hear me? Because I don't see you.
Yes, I do.
So imagine you put your private value. If you put your private value, so this is your real cumulative. This is what happens if you input your real cumulative, and this is what if you lie. But if you lie, you can only increase the probability of the threshold. So it is. So that's the.
I see. Okay. Yeah. Right. Yeah.
So imagine. So usually in many problems, the decision maker. So what is important is what is the probability that the temperature will not exceed 5 degrees, and the decision maker will take his decision with respect to this threshold. So when you are typically in a problem in which the final decision will be based on some threshold A, we don't know this A in advance. This A will be determined by the preference of the decision maker. Then the voter, knowing this, and knowing that the decision will be dependent on this threshold and is impacted by the decision that the decision maker will do, then it is somehow it is dominant strategy for him to reveal the truth. If we take this as the model of preference.
Yeah,
but
I think I
preferred
see.
model, it's fine too. Okay, so now the definitions are this is the main definition, and this is the implication of this definition.
Okay, thank you.
Rida?
Yeah.
Hey, Rida, would you mind explaining to me again, how do I measure a distance in the space C to the peak?
So it's yeah. So read the paper. Okay.
Okay, thank you.
Sorry for that, because I still have 20 minutes and I have many results. I'm sorry. So this is just it's a large space. You should take the integral with respect to some measure on this on zero on, you know. So there is a way to do it. Okay. So but this statement is not completely. You should read the paper. Sorry for that. Arkady, sorry. Okay, let me just give the characterization now. Now if you have in mind Moulin's paper, okay, so it's very close. So what we do is take psi, which is what you want to have is psi. So what you do is you have a formula for capital psi, which is the cumulative associated to small psi. So capital psi is aggregating cumulative distributions. Small psi is aggregating probability. So it's 1-to-1. So if you know this, and vice versa. So now I'm going to characterize capital psi, and how I compute the cumulative for capital psi. It's easy. For every level A, I take the median of the inputs of all the cumulative for all voters, okay, and I add to them n+1 phantoms. And the phantoms are coming from this strictly increasing and right continuous function f1 fn+1 that I will call phantom functions. And unanimity holds if the smallest function is identically equal to 0 and the highest function is identically equal to 1. So it's really 1-to-1 with Moulin's paper, and it's a direct consequence up to some technicalities. It's a consequence of Moulin's paper. So will tell me that's trivial. So fine, but Moulin's paper is not trivial. So the proof is not trivial. So it's like if you have some fixed point theorem, you apply it and you have the result. That's exactly what we do here. So now I'm going to give an example. So this is an example. You have 3 voters. This is for voter 1 cumulative, voter 2 is cumulative, voter 3 is cumulative. Suppose I am unanimous. So the 2 phantoms f1 identically 0. So this is this function. F4 is identically equal to 0. This is this function. So I don't put them here because I don't need them. I need only to take the median between for this function here, and this is another phantom function here. So now I have all my functions. Now I'm going just to follow the median, which is the middle value. So and it gives me this function here. You see. So this is the aggregation. So this function, these 2 black functions are fixed. And once I have the 3 cumulative of my voters, I have the aggregation, and this is one possible method. Okay. So now I'm going to add some axioms. So the first axiom, it's a very basic axiom from the literature on aggregation probabilities. It tells you that if for any Borel measurable set A, if everybody agree that the outcome should be in A, then it should be in A. Or equivalently, if everybody believe that A has probability 0, then the aggregation, then similarly, it should be for the aggregation. So this is preservation of certainty. Okay. And the first result we have, important result, says that level SP and certainty preservation are, so the probability aggregation functions that are level SP and certainty preserving are the ones such that all phantom functions are exactly constant. Okay, so these 2 examples I gave here are not certainty preserving because these functions are not constant. Okay, they change with time. Okay. Now the second axiom I'm going to consider is we'll call it plausibility preservation. It tells you that if some interval has positive probability by all voters, so if everybody thinks that some interval is likely, then the aggregation should also have the same conclusion. The probability of that interval by the aggregation should be also strictly positive. Okay, so this is a property. It's not a standard property in the literature, but I think it makes sense in our case. And we have a characterization for all methods that are level-strategyproof and plausibility preserving. What are these methods? These are the methods such that the phantom functions, okay, are whenever they are not identically equal to 0 or 1 in some interval, then they must be strictly increasing in that interval. Okay, and let me move to the characterization to give an example. So this example here on the right, phantom functions here and here are constant. So it's certainty preserving. It is not plausibility preserving because this phantom function is not equal to 0 or 1, and so it should be strictly increasing, but it is not strictly increasing, it is constant. Okay, so this is not plausibility preserving. This is plausibility preserving because this phantom, I say that I have two phantoms that I didn't draw, which is the minimum one, which is equal to 0, the maximum one is equal to 1, identically 1. So they are constant, but they are equal to 0 or 1. Okay, and whenever it is not, they are not equal to 0 or 1, they should be strictly increasing. So it is plausibility preserving, but not certainty preserving, because to be certainty preserving, phantoms should be constant. Here, the phantoms are increasing strictly. Okay, so now we understand some properties on the aggregation, and we understand them by understanding the behavior of the phantom functions. Now I'm going to characterize all the methods that are certainty preserving, plausibility preserving, and level-strategyproof. Okay. So for that, I'm going to define a set of functions. I'm going to call them order functions or order statistics. They're in Moulin's models in the one-dimensional framework. So these are the functions so that if I give you n values in 0, 1, you output the kth smallest value. The function doing this, I call it the kth order function. Okay, so we have n functions like this. The minimum, the one that output the minimum value, the one that's output the maximum value, the one that, and you may have one that output the median if you have an odd number of voters, for example. Okay. And now I'm going to introduce a function that I'm going to call the kth order cumulative. This is such that I take the kth smallest. Sorry. Question? Okay. There is any question? No? Do you hear me?
Yes, we do.
Sorry. Okay. So here the kth order cumulative is an aggregation function that so we look in the cumulative space. It's going to take for every level A all the cumulatives at A for the voters and take the k smallest value. Okay. So this is a cumulative function, and so it defines a probability. If you go back to the probability space, and I called it the kth order cumulative. And this theorem tells us that the order cumulatives are the unique probability aggregation functions that are level-strategyproof, anonymous, certainty preserving, and plausibility preserving, which are the action that we introduced so far. Of course, there is one particular interesting cases, which are the Middlemost cumulatives. What are the Middlemost cumulatives? These are the one that outputs the median order function if n is odd, and if n is even, you have two possibilities: the smallest or the upper, the lower or upper Middlemost. Okay, and we can show that These kind of functions are welfare maximizers for a certain definition of welfare using the L1 distance to the peak. This is kind of standard results. With the L1 distance, the middlemost is or the median is maximized welfare. Okay, so an example, if I have 3 voters and their inputs are one stochastically dominating the other one, first order stochastic dominance. So they are ordered in that way. You take the median, the median inputs. Okay. So which is somehow you adopt completely the opinion of the median voter here. Okay, for all probabilities. And this is, so you may like it or not. So what we are going to do now is to have to add some to characterize another method that we are going to call the proportional cumulative. And this proportional cumulative will satisfy a property we call proportionality, or you could call it diversity if you like. So what is the property? Suppose that all voters are completely certain about the outcome. So voter I strictly think that is certain that it will be the Dirac mass. So his probability is a Dirac mass at some AI, some event in the scale. So he's sure that it will be some outcome, and they disagree. They are not sure about the same outcomes. Okay. So suppose, so this is, so if all voters input Dirac masses, what should we do? So we may desire that the outcomes is just the average, or the empirical distribution of what they report. Okay, if one voter think that the temperature will increase by 1 degree for sure, and the other one think that it will increase by 2 degrees, then the decision maker will believe that the probability 1/2 it will be 1 degree, probability 1/2 it will be 2 degrees. So this is, if proportionality is satisfied, this is what the decision maker will believe if you use a proportional probability aggregation function. Okay, so this is an axiom, and we may wonder if there are any aggregation function which is Level-Strategyproof that satisfies this axiom. Okay, clearly, if you take the mean of the probabilities, then proportionality will be satisfied, but it will not be Level-Strategyproof. The Middlemost cumulative is not proportional, but it is Level-Strategyproof. Okay, so if you take the Middlemost cumulative and you have 3 voters, one is sure it's A1, the other one is sure it's A2, and the other one is A3, and A2 is between A1 and A3. The output will be the Dirac mass at A2, so it will not be the average. Okay, and this theorem says that there is only one probability aggregation function that is Level-Strategyproof and proportional, and this is given by this formula. So this method, this formula, what is this formula means? This means that you are going to add your phantom uniformly between 0 and 1. Okay, so 0, so we have probabilities, so probability minimal is 0, probability maximal is 1, and here you add uniformly your phantoms, and they will be constant. So the method will be certainty preserving because we have constant phantoms, and also it will be anonymous and unanimous because we use only n-1 values, as you can see here. Okay, so this method, even if you don't use in the axiomatization, certainty preservation, unanimity, and anonymity, it will have these properties. But of course, this method will not be plausibility preserving because, as we have seen before, certainty preservation and plausibility preservation implies order cumulatives, and it's not an order cumulative function. Okay, so let me give an example. I have an example somewhere here, sorry. Yeah, so here we have the example I had before. We have the 3 voters that have their values, one dominating the other. And what we do is 1/3 of the distribution. So these are the phantoms at 1/3 and 2/3. So this here is this value is 1/3. So we follow the leftist voters 1/3 of the mass, and then we are constant, and then we follow the second density function of voters, the middle voters, 1/3 of the 1/3 of the probability, and then the rest of the probability will follow the rightist voter. Okay, that's the aggregation. The middlemost cumulative, it gives us this function here. So you see that these two functions doesn't give the same solution. Okay, so I don't have a lot of time, so I'm going to skip the extension. So we can extend this function. Instead of having voters with the same weight, we can give them weights, and we have a characterization for this, but I'm going to skip it. We can also extend to non-anonymous cases using another formula of Moulin. I'm going to skip it, and I'm going to move to extension to majority judgment. So majority judgment. So now how we can apply these tools to majority judgment. So just so for people who doesn't know majority judgment, I give an example, two examples. So imagine that you have an election, you have political election, and you have two candidates, for example, Hillary Clinton and Donald Trump. So majority judgment, we ask each voter to give to every candidate a grade. For example, here it's great, good, average, poor, terrible. Okay, and then each candidate will have a distribution. Here it's 8% of voters think that Hillary Clinton is great, 27% good, 20% average, 11% poor, 34% terrible. So you can interpret this as a probability distribution over the scale: great, good, average, poor, terrible. So this is the output of the method. And now we are going to rank the candidates using some rule, and the rule of majority judgment is based on the median and iteratively speaking. So it's not the topic to explain exactly what is majority judgment, but the idea is this. So here, these two examples here are coming from a pool done by Pew Research Center. This one was done if you go here, so it was done in 2016 in October, and this one was done in June, just before the election, 2020. So you can see that it's very interesting. In fact, when you look at the data, for example, Donald Trump, you look in 2016 how voters grade him in 2016. His supporters, and in 2020 is much better in 2020 than how he was when he won the election in 2016. And Hillary Clinton has a better evaluation than Biden in 2020, but the outcome was not exactly the same outcome. But it's interesting just to look at the data, and you see that it's really interesting just to look at these results. So let's not move to extension majority judgment. So what is the formal description of majority judgment? It's interesting to compare with majority judgments under uncertainty, which is the method I'm going to introduce after this slide. So in majority judgments, you have n voters that should rank n candidates. How they do that? There is a scale that is fixed by the designer, such as great, good, average, poor, terrible, which is the scale that was used in the Pew Research Center example above. Then each voter will be asked to submit for each candidate a grade in lambda. So Donald Trump is terrible, Biden is great, or the opposite, depending on your task. Output for each candidate will be, we call it the merit profile in majority judgment theory. So it's in fact a probability distribution over the grade. And what is the probability of a grade A? This is the proportion of voters that voted for A. So in this example, okay, 8% of voters give grade to Hillary Clinton. Okay, so we have the output is a probability distribution. Okay, even so now the ranking is based on the median grade. Okay, we compare the median grade. So we compute the median grade for each candidate, and they are ranked by their median grade. We call it the majority grade. And if two candidates have the same majority grade, we look at the closest point to 0.5 where the cumulative disagree, and this will determine how we're going to rank them. So this is basically the description of majority judgment. So now, how works majority judgment under uncertainty? So the beginning, the 2 points here are the same. So what is different is the middle. Okay, So now the inputs or the ballot for each candidate or each voter, sorry, is a probability distribution over the grades. For example, he can say candidate AK is good for sure, Dirac mass for good. And for another candidate, he may think that he will be great with probability 2/3 and terrible with probability 1/3. For example, he may think that that Biden is good for sure, and Trump can be great with probability 2/3, but he can be terrible with probability 1/3 as a president. Okay, so he's more risky. So it's a way to model riskiness with respect to the judgments that we may have on the candidates. And now how we aggregate, where we aggregate the inputs of voters to have for each candidate a probability, okay, or a merit profile, and for that we use the proportional cumulative. Okay. So why the proportional cumulative? So I'm going to explain in the next slide. So what are the good properties? So first, this method will induce a complete order, which there is no Condorcet cycle. It's also it satisfies independence of irrelevant alternatives. This is like in majority judgments. So adding or dropping a candidate will not change the ranking between the other candidates. It is treating candidates and voters equally, so it's neutral and impartial. Okay, and more importantly, if all voters are sure about the quality, the input are Dirac masses, then we have exactly majority judgment. Why? Because of proportionality. If everybody inputs a Dirac mass, then the output should be the empirical distribution, which is the proportion of people that gives excellent, gives good, very good, which is exactly what majority judgment, classical majority judgment is doing. So it's really an extension of majority judgment, and this is possible because we can satisfy proportionality. And there is only one method satisfying proportionality. This is the one I described. Okay. And we are lucky that such a method exists, because otherwise we cannot extend majority judgment to this context. And the last property, which is nice, is that this method is partially strategy proof in ranking. And this is the consequence of level strategy proofness. So here we are using really the two properties of this aggregation of this proportional cumulative. Proportional cumulative is proportional and is level strategy proof. And my last slide is this one. What does it mean partially strategy proof in ranking? This means the following. Imagine you have two candidates A and B. A majority grade is strictly above B's majority grade. So this is the society's majority grade. So the method will rank A strictly higher than B. But I have a voter I whose distribution for B strictly dominated his distribution for A in terms of stochastic dominance. Okay, so surely he prefers B to A. Okay, because he thinks that's his input. So he would like to increase probably B's majority grade, and he would like to decrease A's majority grade. Okay, so the method will be strategy proof in ranking if he cannot increase B's majority grade and he cannot decrease A's majority grade. But this is impossible. No method is strategy proof in ranking. The question is the question is whether it can be partially strategy proof in ranking, and this is the definition. So what we can show is that the method I described, majority judgment under uncertainty, is such that if he can increase B's majority grade, which is something he would like to do, but imagine he can do that, but then he cannot decrease A's majority grade. And if he can increase A's majority grade, decrease A's majority grade, he cannot increase B's majority grade. So he can manipulate, but only in one direction, not in both directions. So here you have two directions of manipulations: increasing B's majority grade, decreasing A's majority grade. So this result tells you that the method I described, if a voter can manipulate and in one direction, he cannot do it in the other direction. That's why we call it partially strategy proof in ranking. And this is the end of my talk. Thank you very much.
Thank you very much, Rida. Other questions?
So let me first come back. Do you want the slide or I show my face? What is better for you?
Your face.
Okay, let's zoom.
Yeah. So, Merale, do you have a question?
No.
Rida, I wanted to ask about the applicability of this majority judgment with
Second part.
uncertainty.
Okay.
Is it applicable? I mean, will voters actually submit probabilities?
In political elections?
I don't know.
I don't
Anywhere.
think, yeah, I don't know. So I think it's better to see it as you know, something that we can use as mathematicians. We can use it to, if we want to hire people in some mathematical department, we may think to use this method, but I don't think general public can use it. So yeah. And also, if you go to the paper, I give a lot of citations. There are lots of people in operations research. For example, the cousin of Peyton Young, his name is Roger. So he's very famous. He's working on putting aggregation of opinions. And these people, so they are not ranking, but they are really, there's lots of people working on, and there are lots of softwares. When you have experts come in to evaluate the risk of nuclear accidents, or for space exploration, some risk that you cannot evaluate. So they ask experts, and they use really methods where the scale usually is linearly ordered, and they are aggregating cumulatives, in fact, and there is a lot of things going on there. So this first part is clearly applicable directly to this context, and there is a lot of people working on that in operations research. The second part, I think it's just a dream. So if, in a sense, that imagine that we are in 100 or 200 years and everybody is very good in mathematics, then perhaps it may be applicable, but not now. Now, political elections, yeah, I don't know. But I feel that the reality is that we are not sure about the quality of the candidates. If you want really to do it well, this is how we should do it. But you can approximate it. You can cross two. You can, for example, in the ballot, instead of crossing one box for great or one box for good, you can cross two boxes, and then we can infer that it is one half this, one half this.
Yeah.
Or one third, one third, one third. So we can approximate the method by doing this trick.
Yeah.
So this is possible.
Yeah.
If you want to do it in practice.
More questions? Okay, so thank you very much, Rida.
Thank you, Hélène.
Thank you.